Welcome to Lesson 4.3, Configuring Training Parameters. Overview. Training parameters can make or break your fine-tuning results. Too high learning rate? Model diverges. Too small batch size? Training takes forever. In this lesson, you'll learn to configure training parameters optimally for your Tesla P40 GPUs. Duration: 45 minutes. Difficulty: intermediate. Learning objectives. By the end of this lesson, you will understand key training hyperparameters, choose optimal learning rates, configure batch sizes for Tesla P40, set up gradient accumulation, configure warm-up and learning rate scheduling, enable memory-efficient training on Windows, set up logging and checkpointing. Key training parameters. 1. Learning rate. How big each update step is. 2. Batch size. How many examples per update? 3. Epochs. How many times to see full dataset? 4. Warm-up. Gradual learning rate increase at start. 5. Scheduler. Learning rate changes during training. This script is designed to fine-tune a language model using the Unsloth library, and it consists of several key steps. First, it imports necessary libraries and initializes the model by loading a pre-trained version of Llama 3.2 3B instruct, setting it up for 4-bit loading to optimize memory usage. The script confirms successful loading with a message. Next, LoRa adapters are added to the model, which enhance its ability to learn from specific tasks without requiring extensive resources. This is crucial for efficient fine-tuning. The script then prepares the training and validation datasets, loading them from JSON files and applying a chat template to format the input correctly. It outputs the number of training and validation examples, ensuring your data is ready for training. After configuring training parameters with training arguments, the script creates an SFT trainer instance, which encapsulates the model, tokenizer, and datasets for training. Finally, it checks GPU properties and starts the training process, monitoring the loss to ensure it decreases over time. Once training is complete, it provides metrics like training time and final loss, confirming the training's success. Create notebooks /03 first training /03 train IPINB. Cell 1, setup and imports. Cell 2, load model. Cell 3, add LoRa. Cell 4, load data. Cell 5, configure training. Cell 6, create trainer. Cell 7, start training, the exciting one. Understanding training output. This output shows the training progress of your model over 3 epochs. Each line under step represents the training loss, learning rate, and processing speed for that specific step. Monitoring the loss is crucial, as it indicates how well the model is learning. Ideally, you want to see this number decrease over time. The learning rate is also displayed, which adjusts how much to change the model in response to the estimated error each time the model weights are updated. As training progresses, you might notice it decreasing, which helps fine-tune the model's performance. At the end of the training, you'll see the evaluation results, including the final loss and the time taken for training. The final loss value is particularly important, as it tells you how well your model is performing on the training dataset. The output confirms that your model has completed training successfully, and you can now move on to evaluating its performance. What it is, how wrong the model is, what to look for. Decreasing steadily. Good. Model is learning. Plateaued early. May need lower learning rate. Jumping around. May need lower learning rate or larger batch. Increasing. Model diverging. Stop and lower learning rate. Typical progression. This output summarizes the training progress of your model. Initially, you see a range of 2.5 to 3.0, which indicates that the model is essentially guessing, showing poor performance. After some fine-tuning, this range improves to between 0.5 and 1.5, reflecting a significant enhancement in the model's ability to make predictions. The final range of 0.1 to 0.5 signifies excellent fine-tuning, where the model is performing very well. However, it's crucial to monitor for overfitting at this stage, as a model that performs too well on training data may not generalize effectively to new, unseen data. Keeping an eye on these metrics helps ensure that your model remains robust and reliable. For Llama 3.23b, 4-bit, average 200 tokens example. Config, VRM usage, speed, recommended. Batch 1, Grad AC 1. HR8 GB, slow, too slow. Batch 2, Grad AX 4. 10 GB, good, safe start. Batch 4, Grad AC 2. 12 GB, better, good balance. Batch 8, Grad AC 1. 16 GB, best, may, on long sequences. Start with Batch 4, Gradient Accumulation 2, effective batch 8. This command outlines the learning rate schedule for training your model. The learning rate is a crucial hyperparameter that determines how quickly the model updates its weights during training. Starting at 2.0 E4 allows the model to learn effectively after the warm-up phase, where it gradually adjusts to the training data. As training progresses, reducing the learning rate to 1.5 E4 in the middle phase helps fine-tune the model's performance, allowing for more precise adjustments. Finally, lowering it to 5.0 E5 at the end ensures that the model converges smoothly, minimizing the risk of overshooting optimal weights. Monitoring these changes in the learning rate is essential, as it directly impacts the model's ability to learn and generalize from the training data. What it is: training speed. Tesla P40 expectations. Llama 3.23b, batch 4, 1.0 to 1.5 it versus Llama 3.18b, batch 2, 0.5 0.8 its. Windows versus Linux, 10-15% slower expected. What it is: loss on validation set. What to look for: lower than training loss, good generalization. Similar to training loss, okay? Much higher than training, overfitting. Training time estimates. Configuration: batch 4, gradient accumulation 2, 2048 max length. Dataset size, epochs, estimated time, Tesla P40. 50 examples, 3, 10 to 15 minutes. 100 examples, 3, 20-30 minutes. 200 examples, 3, 40 to 60 minutes. 500 examples, 3, 90-120 minutes. Factors that affect speed. Sequence length: longer equals slower. Batch size: larger equals faster if fits in memory. Gradient checkpointing: saves memory, costs. 15% speed. Monitoring training. Setting the num_train epochs to 3 means that the model will go through the entire training dataset 3 times. This is an essential parameter because it determines how many times the learning algorithm will adjust the model weights based on the training data. Training for multiple epochs allows the model to learn more complex patterns and improve its performance, but it's important to balance this with the risk of overfitting. In this case, 3 epochs is often a good starting point, especially if you're working with a smaller data set. Adjusting this number can help you find the sweet spot for your specific task, so keep an eye on your model's performance as you experiment. This code sets the training parameter, max steps, to 300, which means the model will train for a fixed number of 300 steps. It's important to note that this parameter overrides the num_train epochs setting, allowing you to control the training duration more precisely. Specifying max steps is particularly useful when you want to ensure that training doesn't exceed a certain limit, which can help manage training time and resource usage effectively. By controlling the number of steps, you can experiment with different configurations without needing to adjust epoch counts, making it easier to find the optimal training duration for your specific dataset and model. This PowerShell command sets up a continuous loop to monitor your GPU performance every 2 seconds. The NVIDIA SMI command retrieves important metrics about your NVIDIA GPU, such as memory usage and GPU utilization. This information is crucial during model training, as it helps you ensure that your GPU is being used efficiently and that you're not running into memory limitations. The Start Sleep Seconds 2 command pauses the loop for 2 seconds before refreshing the output. The Clear Host command clears the terminal screen, making it easier to read the updated stats without clutter. In the output, you'll see details like the GPU name, memory usage, and GPU utilization percentage. This output confirms whether your GPU is actively engaged in training and how much memory is being consumed, which is vital for optimizing your training process. When to stop training. This output shows the evaluation loss for each epoch during your model training process. The evaluation loss is a critical metric that helps you understand how well your model is performing on unseen data. In the first epoch, the loss is 1.5, which is relatively high, but as you progress to the second and third epochs, you see a decrease to 1.2 and then 1.1. This indicates that the model is learning and improving. However, in the fourth epoch, the loss slightly increases to 1.15, which is a warning sign that the model may be starting to overfit the training data. By the fifth epoch, the loss rises further to 1.20, confirming that overfitting is occurring. At this point, it's crucial to stop training to prevent the model from memorizing the training data rather than generalizing well to new data. Monitoring these loss values helps ensure you achieve a balance between training and validation performance. Action. Stop training. Use checkpoint from Epoch 3. This code snippet sets up the training parameters for fine-tuning a language model using the Transformers library and Unsloth. The training arguments class is essential as it defines how the training process will be conducted. You'll notice the output diar specifies where to save model checkpoints, ensuring you can resume training or evaluate later. The numTrain epochs is set to 3, meaning the model will see the entire dataset 3 times, which is crucial for learning. Batch sizes are defined for training and evaluation, and gradient accumulation is used to effectively increase the batch size without requiring more memory. The learning rate and its scheduling are configured to help the model converge smoothly. Memory-efficient optimizers like AtomDO 8-bit are specified to optimize performance, and precision settings adjust for hardware capabilities. Logging and evaluation strategies are included to monitor progress, while checkpointing ensures you don't lose your work. Finally, a reproducibility seed is set, and the output confirms that the training configuration was successfully created. This structured setup is vital for effective model training.
Here's a different failure mode, not overfitting, but stagnation. Loss at step 50, 1.2, step 100, 1.15, step 200, 1.14. The curve has gone. If this happens early in training, the learning rate is too low and the optimizer is taking steps too small to escape a plateau. Restart with a higher learning rate. If it happens late in training, after a healthy decline, congratulations, the model has converged. There's nothing left to squeeze out. Save it and move on.
This is the undertraining signature. Training loss only drops from 3.0 to 2.6, and validation loss barely moves from 3.1 to 2.7. Both numbers are high, and neither is improving meaningfully. The model hasn't learned enough.
This could mean you need more epochs, a higher learning rate, a higher LoRa rank to give the model more capacity to learn, or a closer look at your dataset. Noisy or inconsistently formatted training data produces exactly this kind of plateau.
The remedies for undertraining are the mirror image of overfitting fixes. Train longer, raise the learning rate, increase LoRa rank, or improve data quality.
The loss curves tell you which problem you have, then you know exactly which lever to pull.
Quantitative evaluation.
The batch test function runs your entire test suite through the model in one pass.
For each test case, it constructs the extraction prompt from the input field, calls your model function to generate an output, and packages the result, name, input, output, and expected fields into a results list.
After the loop, it prints every result in a structured format so you can scan all inputs and outputs at once. This batch view is what separates rigorous evaluation from cherry-picking a single impressive example.
Try these solutions in order. First, reduce per device train batch size to 2 or 1. Second, increase gradient accumulation steps to compensate, keeping the effective batch size the same. Third, reduce max X length to 1024. Fourth, confirm gradient chick piking to co is set. If it isn't, enabling it alone often resolves the issue. After making changes, restart the kernel before
This code snippet configures the evaluation strategy for your model training. Setting eval strategy to steps means that the model will be evaluated at regular intervals during training rather than just at the end. This is important because it allows you to monitor the model's performance and make adjustments if necessary, ensuring that it is learning effectively. The eval steps parameter specifies that the evaluation will occur every 25 training steps. This frequency strikes a balance between getting timely feedback on the model's progress and not overwhelming the system with too many evaluations. By keeping an eye on the evaluation metrics, you can catch potential issues early and optimize your training process.
This output shows your model scoring in the high 80s and 90s across all test cases with an average of 91%. That average is the headline number, but the per case breakdown is where the real information lives.
A case scoring 60% while others score 100% tells you exactly which scenario needs more training examples.
A uniformly high score across simple and complex cases alike means your model has genuinely learned the task, not just the easy version of it.
The cause is almost always a learning rate that's too high. The fix: drop it by half or more, from 2E4 to 1E4, or all the way to 5E5 if needed. Also increase warm-up steps from 10 to 20, which gives the optimizer more time to stabilize before hitting full learning rate. Finally, audit your training data for corrupted examples. A single malformed sample can produce a gradient spike large enough to trigger NaN on its own. If the progress bar never moves and your GPU sits at 0% utilization, training has stalled before it started. The most common culprits on Windows are a data loading issue, a tokenizer problem, or a file access conflict with the NTFS file system. Diagnose in this order. First, print the length of your training dataset to confirm it loaded correctly. Second, set data loader numWorkers equals 0 in training arguments. Windows doesn't support multiprocess data loading the same way Linux does, and this single change fixes the stall in the majority of cases. Third, restart the kernel and rerun from scratch. Right now, the model produces unstructured natural language. After fine-tuning on structured data, that same prompt will produce clean, well-formed JSON like this.
Quantitative scores tell you how often the model gets it right. Qualitative evaluation tells you how it fails when it gets it wrong.
This JSON dataset, 3 people with names and ages, is the kind of ground truth you feed into a qualitative check.
You know exactly what the correct output should look like for each entry, which means any deviation is immediately visible. Structured ground truth like this is what makes qualitative evaluation systematic rather than impressionistic.
Complete loading script with save strategy steps and save steps 50. The trainer automatically writes a checkpoint every 50 training steps. Here's what that directory structure looks like on disk.
This code sets up the training parameters for fine-tuning your model with unsloth. The output dir specifies where to save the model outputs, which is essential for tracking your progress and results. The numTrain epochs is set to 3, meaning the model will go through the entire training dataset 3 times, which helps improve its performance. The per-device train batch size of 4 indicates how many samples will be processed at once, while gradient accumulation steps of 2 allows you to effectively double your batch size without increasing memory usage. The learning rate is set to 2E4, which controls how quickly the model learns, and using a cosine learning rate scheduler helps adjust this rate over time for better convergence. The warm-up steps and logging steps parameters help manage the training process by gradually increasing the learning rate initially and logging progress every 10 steps. The evaluation strategy is set to check performance every 25 steps, and the model will save its state every 50 steps, with a limit of 3 saved models to manage storage efficiently. Using AtomW 8-bit for optimization reduces memory usage, while enabling FP16 allows for faster computations with half-precision floating points. Finally, gradient checkpointing helps save memory during training by storing only a subset of intermediate results. Overall, these configurations are crucial for optimizing your training process and ensuring efficient resource use.
Beyond automatic checkpoints, you can save manually at any point by calling model.saveTissueTrained and tokenizer.saveT. This is useful after a manual quality check, when you've run inference, liked what you saw, and want to lock in that exact state before training another epoch. The call produces no terminal output, but the output directory will contain the adapter weights and config files you need to load the model later. Check that the folder exists and is non-empty before closing your session. Complete training notebook. Save this as notebooks/03firsttraining/03train.ipb, your complete self-contained training notebook. This is the full pipeline in one place. It opens with imports and a confirmation print so you know the cell executed. The model loads from unsloth/llama 3.23b instruct with 4-bit quantization enabled. That's the memory optimization that makes this possible on 24 gigabytes. LoRa adapters are applied next, dramatically reducing the number of parameters that the training and validation datasets load from your JSON files. A formatting function applies the chat template to every example, and the dataset sizes print so you can confirm nothing was silently dropped. Training argument sets batch size, learning rate, evaluation strategy, and all the other knobs you've configured. SFT Trainer wires the model, tokenizer, and datasets together. When it finishes, the model and tokenizer save to your output directory, ready for the next lesson. Training completion checklist. Before calling this training run done, verify 4 things. First, training completed without a Python exception. An error mid-run means your saved checkpoint may be incomplete. Second, your final training loss is below 1.5 and the validation loss isn't dramatically higher. That gap is your overfitting indicator. Third, your output directory contains checkpoint folders and the final model weights. Open the folder and confirm the files are there. Fourth, your training logs are saved for reference. If all 4 check out, you're ready for lesson 4.5, loading this model, running real queries against it, and measuring how much it actually improved. What's next? The model is loaded, quantized, and fitted with LoRa adapters. The foundation is solid. The next piece of the puzzle is the data, specifically how to format and prepare your training examples so the model learns exactly what you want it to learn. That's lesson 4.2, preparing your training data. Additional resources. For deeper reading, the Unsloth documentation covers every parameter of fast language model in detail. The original LoRa paper by Hugh et al. Explains the mathematical foundation for why low-rank adaptation works. The Q-LoRa paper by Detmers et al. Is the source of the 4-bit quantization approach used here. And the pfeat library documentation from Hugging Face covers the broader ecosystem of parameter-efficient fine-tuning methods that LoRa belongs to. Additional resources. For deeper reading, the SFT Trainer documentation covers every training argument in detail. The Unsloth Training Tips page has hardware-specific guidance. And the Debugging Training Guide is worth bookmarking, It covers edge cases that go well beyond what any single lesson can address. You've just trained your first fine-tuned model. That's worth a moment to appreciate before moving on.
This image illustrates different learning rate schedules in a comparison chart. Here, we see three distinct approaches to manage the learning rate during training: cosine decay, linear decay, and a constant learning rate. The green line represents cosine decay, which is recommended for its effective balance in adjusting the learning rate over time. You'll notice it starts high, allowing for rapid learning, and then gradually decreases, helping to refine the model. The blue line denotes linear decay, which decreases the learning rate linearly as training progresses, and the orange dashed line represents a constant learning rate that remains unchanged during training, which might not be as effective for many situations. Understanding these schedules is crucial because they influence how quickly your model can converge on patterns in the data and avoid issues like overshooting the optimal solution. For your next steps, consider experimenting with these different learning rate schedules in your own fine-tuning process, starting with the cosine decay as it often yields the best results. This image illustrates the effect of low-rank adaptation, or LoRa rank, on training loss as the training progresses. Each line represents a different rank value, with the varying colors indicating ranks of 4, 8, 16, 32, and 64. You can see that as training progresses, the loss decreases for all ranks, but they do so at different rates. The rank value significantly influences how quickly and effectively the model converges. For instance, the lines for ranks 4 and 8 show a much more rapid decline in loss early on compared to higher ranks, particularly rank 64, which improves more slowly. This indicates that lower ranks might allow for faster training convergence, while higher ranks may offer slower improvements, possibly due to a more complex model learning larger parameter adjustments. Understanding these dynamics is critical because it helps you determine the optimal rank for your own training scenarios. As you proceed with your fine-tuning, experiment with different rank values within your own models to see how they affect training loss and convergence speed. This is a great way to refine your approach and enhance your model's performance. This image explains gradient accumulation, specifically how to simulate large batch sizes while working with limited video RAM. Here, you see a simulated batch size of 16 that is achieved by breaking it down into smaller micro batches of 4, as indicated by the gradient accumulation steps set to 4. In this setup, we accumulate gradients over those 4 microbatches before performing an optimizer step. This pattern allows us to effectively manage memory usage while still leveraging the benefits of larger batch sizes. You begin by processing the first 4 samples to gather their gradients, then move to the next 4, accumulating each time until you've processed all 16 samples. Once you've accumulated gradients over the 4 microbatches, you execute the optimizer step, which updates the weights only after processing all 16 samples. This method is crucial when you're facing VRAM constraints, as it allows you to keep training performance high without overwhelming your hardware. As you move forward, try to implement this strategy in your own training loop and monitor how it affects performance and memory requirements. This approach will become a valuable tool in your fine-tuning workflow. This image shows a heat map illustrating the hyperparameter sensitivity, specifically focusing on the final training loss for various combinations of batch sizes and learning rates. Each cell in this grid represents the loss value achieved with a particular pairing of these two hyperparameters. The left side of the chart details the learning rates, ranging from 5E5 to 3E3, while the bottom axis lists the batch sizes from 4 to 32. As you observe the values, the lower the loss, the better the model's performance. You can see that the combinations yielding the lowest loss values, like 0.52 and 0.55, are associated with smaller batch sizes and moderate learning rates. Understanding this heat map is crucial as it helps you identify the most effective hyperparameter combinations for fine-tuning your model. By selecting these optimal values, you'll increase the likelihood of achieving better performance in your training. The next step is to experiment with the hyperparameter combinations that have shown the most promise here, and apply them to train your first model using the Unsloth library. This image illustrates the warm-up learning rate schedules used during training. You're seeing two key methods here. The blue line represents a linear warm-up with a constant learning rate, while the green line shows a linear warm-up followed by a cosine decay. The purpose of the warm-up phase is to gradually increase the learning rate from 0 to its initial value, preventing large weight updates in the early stages of training. You'll notice that the blue line levels off after the initial ramp-up, maintaining a constant learning rate. In contrast, the green line shows how the learning rate decreases after reaching its peak, which helps fine-tune the model as training progresses. The dashed orange line indicates the endpoint of the warm-up period, set at step 30 in this scenario. Understanding these schedules is crucial because they impact how effectively your model learns. For your next steps, consider experimenting with these different warm-up strategies in your training process. Tuning the learning rate can significantly affect your results, so it's worth testing to find what works best for your specific model and dataset. This image displays two graphs comparing LoRa rank to both quality and the number of trainable parameters. On the left, we see the relationship between LoRa rank and relative quality percentage. As the rank increases from 4 to 128, the quality improves significantly, leveling off around 100%. This indicates that using a higher rank can enhance the performance of your model, but after reaching a certain point, the quality gains diminish. On the right, we have the graph illustrating LoRa rank against the count of trainable parameters. Here, you can observe a more gradual increase in parameters as the rank rises, particularly experiencing a spike at rank 32. This suggests that while a higher rank may improve quality, it also increases the complexity of your model through a greater number of trainable parameters. Understanding this balance is crucial. You want to find an optimal rank that gives you the best quality while managing the number of parameters for efficiency. As you proceed, consider experimenting with different ranks based on these insights to achieve your desired outcomes in fine-tuning. This image provides a comparison of different optimizers for fine-tuning large language models. Each optimizer has unique characteristics that can significantly impact your training process. Starting with Atom W 8-bit, it's low in memory usage and offers fast performance, making it an excellent choice for Q-LoRa training, which is commonly used. The Atom W 32-bit variant, while also fast, demands higher memory, so it's better suited for full fine-tuning operations when you have at least 40 gigabytes of VRAM available. Next, we have SGD with Momentum, which is the fastest in terms of speed, but might require a slower start in terms of convergence. This makes it a solid option for continued pre-training tasks. The Lion optimizer is low in memory and fast, and it's considered experimental, sharing similarities with Atom W, which could be interesting to explore. Finally, Adafactor uses the least amount of memory, but features a moderate speed and convergence, making it ideal for setups with strict memory limitations. Understanding these differences is crucial as they allow you to choose the optimizer that best fits your specific hardware and training objectives. Next, take some time to evaluate which optimizer aligns best with your project needs before diving into the implementation. This image presents a comparison of batch sizes and gradient accumulation strategies for training machine learning models. It provides a clear breakdown of how the effective batch size is calculated based on the number of devices, the gradient accumulation steps, and the number of GPUs you have. You can see several configurations listed, detailing the values for per device, grad accum, and the resulting F batch. For instance, with one device and a gradient accumulation of 4, you achieve a small effective batch size of 4, which is the minimum safe configuration. As you scale up, such as using 2 devices with 4 accumulations, you get an effective batch of 8, which is a recommended starting point. The VRAM required increases accordingly, making it crucial to match your batch and accumulation settings with the capacity of your GPUs. The note on the sweet spot indicates that using 4 devices with 4 accumulations gives optimal performance on common GPUs. Understanding these configurations helps you effectively manage your resources and train models efficiently. Next, you should try adjusting these parameters in your training scripts to find the best setup for your specific tasks and hardware. This image illustrates the learning rate finder, a crucial tool for fine-tuning your model's performance. The graph showcases how the loss changes in relation to various learning rates, plotted on a logarithmic scale. Notice the curve where the loss decreases initially, but then starts to rise sharply. Your focus should be on the highlighted area, which indicates the optimal learning rate range. Specifically, you're looking for the best learning rate, roughly around 2E4, which is just before the loss reaches its minimum. Selecting a learning rate within this optimal range can significantly enhance your model's convergence speed and overall performance. Using this technique, you ensure that your model starts training effectively, avoiding issues like slow convergence or divergence caused by a learning rate that is too high or too low. So, take note of the best learning rate identified here, and in your next steps, implement this value in your training configuration. This is a foundational skill in model training that will serve you well as you continue to experiment and refine your approaches. This is a quick reference guide for configuring the training parameters in your LLM fine-tuning process. Each parameter is crucial for optimizing your model's performance while managing resources effectively. Starting with the per-device train batch size, it's set to 2 to conserve VRAM. If your system allows, you can increase this for potentially faster training. The gradient accumulation steps is set to 4, which helps compensate for the small batch size, allowing you to mimic a larger batch effect effectively. The learning rate of 2E4 is standard for LoRa. If you encounter instability, you might adjust this to 1E4. You've got num train epochs set to 3, which is a good starting point, but typically, you might find a range of 1 to 5 works best for different scenarios. The warm-up ratio is at 0.03 to provide a gentle increase in learning rate during the initial steps of training, which helps stabilize training. For dynamic learning, the LR scheduler type is set to cosine, ensuring a smooth decay of the learning rate. The BF16 parameter is true since it optimizes memory usage effectively on Ampere Plus GPUs. Gradient checkpointing is also enabled, saving VRAM at a slight speed cost. The optim parameter is AtomW 8-bit, chosen for its memory efficiency. You'll log training progress every 10 steps, with checkpoints saved every 100 steps. Finally, max-sec/length is set to 2048, which defines the clip limit for your sequences. These configurations will contribute significantly to a successful fine-tuning process, so be sure to adjust them based on your specific requirements and monitor performance as you train your model.